So now let's talk about the noble gas configuration stuff and how electrons want to become stable, like those noble gas electronic configurations. So, for example, if you
Show
have
us where the noble gases are.
so the noble gases are in the last column of the periodic table. So okay, they're in the last column of the periodic table. So this whole thing, all of these are noble gases, and they usually have a oxidation state of zero. Of zero means meaning that they're really stable. They don't want to gain or lose any electrons. So usually atoms they want to usually tend to go into this inert gas configuration. So like for example, if you have magnesium, for example, magnesium, its last subshell would be one, two, three. So it's in the third quantum. So its last subshell would be three s2, right? Three s2. So in order to go into the noble gas configuration, it has to lose these two valence electrons, and so it's usually its
Because
valence.
it's two away from the nearest noble
Yeah,
gas.
because it's two away from the noble gas, which
Neon.
is neon. So its valence charge would be two minus, and that works for almost this whole row, right? And also because it's like uh, two boxes away from the noble gas, and it works for this first column too, which is it only wants to gain one electron. I mean, yeah, lose one electron. No, gain one electron. No, lose one electron. My bad, because it's in the not metal part of the section of the periodic table. So it wants to gain one electron. It wants to lose one electron, so it could be a plus charge. Okay, so it would have a 2 plus charge. And like carbon, for carbon, it would have a plus 4 charge because it's 4 boxes away from the nearest noble gas configuration.
What about titanium?
Titanium. Titanium, since isn't this part of the electronic, so it wants to go actually 2. Since instead of going like 5 boxes to the right, to the to the neon, to the electronic, to the noble gas electronic configuration, it actually wants to go backwards left and go
Why?
1, 2, 3. Since it jumps less, so 1, 2, 3. So it wants to gain
So it
negative.
skips the D?
It wants to gain a -3 charge. So its valence charge is usually -3.
So it skips this, the D?
What do you mean it skips the D? It doesn't
Look,
skip
you
the
said
D.
1, 2, 3.
No, this is just for this whole column because they place these columns for a reason. Like the groups of a periodic table isn't usually in columns. Like for the noble gas configuration, like
Wait,
each of
pause
this
it, pause
column
it.
has like similar characteristics.
Alright,
That's
pause
why
it.
they put it in a column. Okay, whatever. What were you gonna say?
Okay, look. You were like 1, 2, 3, right?
Yeah.
So I just skip all of this.
Because I told you, like the columns of the periodic table have similar characteristics. So if this once again 3, then the whole column want to do the same thing.
So how about we have an element like gold, for example?
Yeah, that's in the transition levels. It doesn't. You can't figure out the characteristics.
So it's only for the SP?
Yeah, SP.
Oh, it's all good. Let me see.
Okay, started.
Okay. Okay. So let's pick an element for globe. An element. This element will be Zn. Fuck this shit.
Just forget it. Just keep on going.
Sure, I won't do it.
Just keep on going. Just
I'm
keep
not
on
sure. I'm
going.
not sure myself. Come on, just wait.
Just keep on
Wait, let
going.
me see something. Okay. What the hell?
Just keep
Chill,
on
chill,
going.
wait. What the hell? Wait, look. You know how we skipped this before?
Okay.
No, I
just-
want to ask you.
Hmm?
You know how we skipped this before?
Yeah. How?
No, like when we were
What are you
fine,
talking about?
like the common chart, like GE for example. It's 1, 2, 3,
I
4.
mean, just forget it. I'll make the video.
Wait, let me ask you.
Hold
Look,
on. Just wait.
first do it normally.
No, because I could do it both. Because then you have
Okay,
to use the
yes.
argon. Huh? Stop. Should I do it or you should?
You should.
Come on. Okay.
Go.
So, if you have zinc, you can also write the, like, so let's write the electronic configuration of a zinc ion. So, in order to do that, to write the electronic configuration, since it's a +2 charge, we could first, since zinc has since the noble gas configuration, you would have like the same 1s2, 2s2, 3s2 up until the noble gas configuration. You could just write the noble gas configuration, it's closest to the noble gas configuration in brackets like this, and then you could write the next electronic configurations. Like for example, it's in the fourth quantum, so you write 4s2, and it's in the last column. Is in the last column of the subshell, so you write 3d10 because you subtract 1.
So we count the D when it's in the last one.
Yeah.
Time.
So it's 3d10. Yeah. So since it has a +2 charge, +2 means it lost 2 electrons. So you need to take away 2 electrons from the outermost subshell. So the outermost subshell is the 4s2 because 4 is greater than 3. So you just subtract the 4s2 from here, and then you have its electronic configuration would be argon in brackets and 3d10. Thank you very much. This is Fall Academy signing out. Okay, hello everybody. So let's say we're supposed to figure out how many occupied outer shells orbitals does an arsenic atom possess. Let's say we're supposed to figure out how many occupied orbitals does an arsenic possess. So basically you just write the boxes that we did before. So its outermost subshell would be 4. Since it's in the fourth quantum, its outermost subshell would be in the p subshell. And then you know that the number of orbitals is the number of electrons divided by 2. So the number of columns, you just count the number of columns and divide it by 2. So it will have 3 boxes. 1, 2, 3. And you use the off-bath rule. So you fill out all of the up electrons first. No, off-bath principle. So you fill out all of the up electrons first, which is 1. Since AS is it has 3 electrons. The outermost shell, which is 4p3, has 3 electrons. 1, 2, 3. You see, its outermost subshell is 4p3 and it has 3 electrons. So you fill out the off-bath rule. So you put
4s.
no, the 4s2 is not the outermost subshell. P is the highest subshell. Right? So you fill out all the up electrons first. 1, 3, and since there's no more than 3, you just leave it like that. So it fills out all three. So it fills out all 3 parts. It fills out all 3 orbitals. So if it was instead 4, you would add a down electron here. But then it's not 4. So thank you very much, and have a nice. You're right. Thank you. And also, oh my bad. last video I made a mistake. It fills out 4p3. 4p3. Since its highest quantum is 4p3, its highest outer shells is 4p3 and 4s2. And s2, if you count the number of columns and you divide it by 2, it will have only one box. Since 2 divided by 2 is 1, right? So it have 2, and then you fill out the electrons. Since it's 4s2, fill out 1 electron, 1 up electron here. Wait, is it 4s2? 1 electron here and 1 down electron here. Wait, hold on. Okay, so I made a mistake from before. Since the boxes represent the orbitals. Since the boxes represent the orbitals and the highest outer shells is 4s2. 4s2 for the arsenic atom, 4s2 and 4p3. You fill out the boxes. Since all 3 boxes is filled up for the 4p3, and both 2 electrons is filled up for the s orbital, then you count the number of boxes. The occupied boxes, which is 1, 2, 3, 4. So it would have a total occupied outer shells of 4. I hope you understand that. Thank you very much.